Okay. This looks good in audio. Test speakers. Okay. Like that. Oh. All right. Where do we start? Exam 6, Chapter 17 review. We go through the version 1 review document, whatever is bothering you. And then I want to pull out some version 2 things because I think they might be useful. Oh. But I didn't give you a copy of those, so you have to write, I guess. Okay. Or I can give you a copy. No problem there. I got plenty. Let's see. Version 1. Here's version 2. I just didn't want to overload you guys. You won't have to write as much. Okay. So is there anyone in particular that's giving you trouble?
Should I go over 27?
All right. I laid out the version 2.
Version 2?
Yeah, because I want to dig into a few of them, but it's not something that you have to labor over.
That's good news.
Yeah,
Hard enough time with
version 1, man.
Oh my goodness.
I
feel like the worst student this semester ever.
Sarah wants to look at number 27.
Oh my goodness.
Okay. So we're given this reaction. And temperature is might as well go ahead and convert it. Okay. Now, what's the question? Well, we're given some other information also. We're given heats of formation, and we're given standard entropies for each of the compounds or elements in that reaction. My guess is that this problem was multiphasic before I split it apart into separate groups. So it wants us to calculate this one. So what would that be? Well, actually it's fairly simple. The standard entropy for this reaction is the entropy of the products minus the entropy of the reactants. Okay? All right. So we need products will be 4 times whatever NO2 is. NO2 is 239.9. And notice entropies are reported as joules per K mole, whereas most enthalpies are kilojoules. Right? So you have to be careful with those units when you start to do other calculations. This calculation is no problem because it's all in entropy. And we need to multiply that value times 4 because this is 4 moles and this is per mole. Then we have oxygen. And remember, for entropies, everything has a value. There are no zeros in entropies. Unlike enthalpies, elements in their standard states have enthalpies of 0. But entropies always have a value. Then we want to add the oxygen, which is 1. 1 mole of oxygen and its value. Joules per K mole. Okay. Then we'll subtract the entropy of the reactants. And that's N2O5. Joule per K mole. There's only one of them there. Okay? So this cancels the moles for each one. Okay. So now the enthalpy, the entropy will be reported in units of joules per K. And that's for the entire reaction. Let's see what I get in my calculator. 239.9 and then 204.8, add those together. And we subtract 2 times this one.
Did you do the,
I'm sorry?
did you do 4 times 239?
Uh-huh.
Okay.
Yeah. And then subtract. So I get 453.76 joules per K. Let's see. Okay.
Did you have that one up there when you're gonna do 28 since they kind of flow into each other?
Oh, yeah, it's the same equation. And we're looking for 28, we're looking for delta G, right?
Mhm.
Delta G. Okay, this one is a little more involved. So,
What's the, for 27, the delta H, is this the change in heat?
that's enthalpy, yes.
Or enthalpy?
Uh-huh.
So we just calculated the change in enthalpy just using the entropy?
No, we calculated entropy
Well,
because that's all that was asked for in 27.
which,
Calculate this one.
well, the answer says calculate enthalpy for the reaction.
27?
Yeah, delta H.
Let me see.
That's what I'm asking.
Oh, wait a minute.
Were you on version 2 or version?
Oh, you're on version 2.
Oh, yeah.
We're on version 1.
Did I hand that version 2 or 1? Today I gave you version 2.
Oh, are we reviewing through?
We're doing version 1 first. You have a copy of that, don't you?
Yes.
Okay.
What's going on here?
But we are going to do.
So what's the difference between version 1 and version 2?
It's just a different mix. But I do want to get into version 2 a little bit because I think some of them, like that one, if we were to do 27 from version 2, that would give us information that we could use to calculate delta G for 28. So I'm going to leave that one up there because we're going to need that information. So for this same equation, the question then is, what is delta G? Well, we're given information for enthalpy and for entropy. And we can calculate delta G if we know these two. Okay, so we got that one, and we got the temperature. So now what we have to do is find out what the enthalpy is for that reaction. And we use a similar calculation. In this case, delta H equals, I'm sloppy. This is for products. Minus the sum of the delta H's for reactants. Let's see. Yeah, you can still see them. So we need, and a delta H for this element, oxygen, is going to be 0. So we don't have to include that one. We just do 4 times the NO2 for products. Which would be 33.150 kilojoules per mole minus 2 times N2O5 delta H. Okay, and that will give us delta H, standard delta H for this reaction.
Why, I know I've asked this before, but why didn't they put the little degree sign after the letters?
These are standard conditions,
The little, just.
standard temperature and pressure.
Standard.
Yeah.
Conditions.
Mm-hmm. So that's the standard delta H for that reaction, if I did my calculations correctly. And then delta G, we solved this equation for delta G. So delta H is going to be this, but that's kilojoules, right? So it has to be, I just do it like this, times 10 to the third joules.
Just to refresh my Greek there, that's
Sigma.
sigma for sum.
That means summation, yeah.
So the sum of the,
The delta H is for products, minus the sum of the delta H is for reactants. In this case, we've only got one of each. That's why I've only got one here and one here. This is going to be, temperature is 298 K. And then the delta S we calculated earlier, 453.76. And this is joules per K. So K's will cancel. It leaves us with joules. So let's see, 298 and 453.76. This one is 1 point. Ten to the 5 joules. And this one is 1.10 times 10 to the 5th joules. I get minus 2.5 2 times 10 to the 4th times joules. Let's see if that's the same as here. Oh, okay, so they want kilojoules. Right, so kilojoules would be this number times 10 to the 1st, correct?
Yeah.
So this would be minus 2.52 times 10 to the 1st kilojoules. And I think the,
well, they have it as 25.2.
right, 25.2 kilojoules. There we go. All right, so is that reaction spontaneous as written? I know that's not one of the questions in the problem, but
Let me see if I can remember to tell me. A negative number is not spontaneous.
well, it's only two possibilities. Either it is or it isn't. No, negative delta G is spontaneous.
It's spontaneous.
Yeah.
50-50. I am willing to guess.
You might be thinking of a positive entropy
Maybe so.
for
Okay. So negative G.
a positive delta S for the system is spontaneous. I like delta G better for spontaneity.
So negative values
delta G
Mhm.
are spontaneous.
Yes.
Now, I have a question on version 2,
Uh-huh.
on number 28. Would that be the same answer because it says, the reaction is allowed to proceed until all substances involved have reached their equilibrium concentrations? Under those conditions, what is the delta G for the reaction? Is that the same answer? I mean, it just reads a little differently.
Oh, no, you're right. It's different.
Which one?
The key there is equilibrium.
It's the same number, it's the same information, but it's
Right.
a different type of question.
This is delta G 0, which tells you if the reaction is spontaneous. But the actual delta G for the reaction at equilibrium is 0. Delta G at equilibrium is 0 because there is no push of any kind to move the reaction in either direction. So delta G would have to be 0. So maybe I should put, up to this point, we're in version 1. And that was version 2. Right, the key to that question is equilibrium. Okay.
About 31.
31. Okay.
The F, that means formation, so the enthalpy of formation.
Yeah, the enthalpy of formation would be minus 20 point what? It's just 20? Oh, 20 kilojoules per mole.
Not negative 20.
Negative, excuse me, negative, right, it's exothermic. And the entropy, standard entropy, is 209 joules per kmol. In 204. Is that thing?
So we need to calculate which thing here.
Oh, all right. I thought I was seeing double. N204 liquid followed by N204 gas. And then we want to know at what temperature is the vaporization of N204 liquid spontaneous. Okay, so here's the reaction that we're interested in. The consequences. We're looking at vaporization of this liquid to that gas.
So would this be another calculate the G? Or just use,
I guess that's one approach.
or would you just do entropy?
Yeah, the way I approached it here, I used entropy. Let's do that way first, and then we'll think about delta G and see if that has an application. So the delta H formation, I don't know why that should have been under standard conditions. Anyway, this is given information. Okay, and this one. And that's not to say that we need all of that information. But what it will tell us is this minus that is the delta H for this one. Minus the minus 20. Oh, wait a minute. It's not right. One's joules and one kilojoules.
No, they're both kilojoules. Negative 20 kilojoules for the liquid
Oh,
and 10 kilojoules
yeah, I left the K out.
for
Sorry.
the gas.
So that's 30 kilojoules per mole, which means this is endothermic. Now that's not necessary to answer the question, I don't think. But that makes sense. To go from a liquid to a gas takes energy. So you gotta put heat into it to make it vaporize. But to answer the question, what we need is the delta H for the system. I mean delta S, excuse me. Delta S for the system. So in that case, we have this one minus this one. No, that should be joules. Yeah, point the right K. It's joules. Okay. So now that would be this one minus that one, which should be 95 joules per K mole. Okay, that's a positive delta S for the system. And then once we know the delta S for the system, we need to relate the system to a temperature. So we did have to calculate both of them because I was going to use delta S for the system is equal to delta H for the system divided by temperature. And that should be in useful information.
It is, I think, down there towards the bottom corner. Well, I mean, there's surroundings.
That's surroundings. Oh, okay. That assumes. All right. What we're saying here is this is the one that's given. Surroundings equals delta H. Surroundings divided by T. And remember, if you have a system and surroundings, anything that happens here is the opposite of what happens there. Okay, so that's why all we have to do to find the system is change the sign.
Okay, can we pause there just for a moment?
Say again?
Can you pause just for a moment while I
Yeah, sure.
a couple of those down?
And the reason for this, well, universe, I should say total, equals delta S for the surroundings plus delta S for the system. Okay? So the total S is going to be some value, but if we're at the vaporization point, then delta S total is 0. Because we're at an equilibrium position. If we're at vaporization of a liquid to a gas, that's equilibrium until all the liquid's gone. Right? That's why the boiling point of a liquid stays the same until all the liquid's gone, and then it starts to go up again. Remember that? Okay. Don't remember that? Our diagram for, let's see, if we have a solid until it reaches the melting point, then the temperature stays the same until we get rid of all the solid. Then it goes up again. This is liquid. And then at this point, it's our boiling point. And then once we got all the liquid gone, we heat up the gas. Okay. So here we are for this one. And at the boiling point, the temperature is constant. That's a sign of equilibrium. And in an equilibrium state, the delta S total is 0. So that means delta S surroundings plus delta S system is equal to 0, and that's why this one is just the opposite sign of that one, because they have to equal to 0.
So back to our problem then.
Oh, okay.
We have,
We'll use this one because we want to know what the temperature of the liquid is while it's boiling.
so we're just going to put our numbers in and solve for the temperature.
So
So temperature will equal the change in
this one
enthalpy divided by the change in entropy.
equals 30. Now, this is kilojoules and this is joules. So this one has to be 30 times 10 to the third joules per mole. Okay? Divided by temperature. So temperature then will be 30 times, that's 30,000. Divided by 95.25. I get 315 K. So that should be the boiling point of this
So,
liquid to that gas.
we changed the kilojoules to joules.
Oh, centigrade. I'm sorry. K minus, yes. This one was kilojoules per mole. So we changed it to joules because the units here are also joules. They have to match. So the moles will cancel and the joules will cancel. Leave us with K. And then we need 42. Is that right? 42 degrees centigrade.
42.
Yeah. Now you were asking if we could calculate delta G for this one. We need,
Well, not if we could, but would it be a useful or necessary step to answering the question? I guess is where
actually it wouldn't answer the question because it wouldn't tell us the temperature.
Right.
In fact, we need the temperature to calculate delta G.
Right.
If we knew delta G, then we could input into the delta G equals delta H minus T delta S and find out what T is. But this is the most efficient way. In fact, I don't know of another way.
So above 42 degrees Celsius, the vaporization of N2O4 liquid is spontaneous.
Right. You're wondering what that really means?
Yeah.
At 42, we're saying that the process is in equilibrium. In other words,
Over there at the
it goes backwards and forwards.
boiling point line.
Yes. It would just stay right here and not move. But if we increase the temperature above 42, then we're adding enough energy to overcome that equilibrium and go that way. We're saying in order to find out what T is, we need to assume equilibrium. That's why this is 0. And that's why this one and that one are opposite signs of each other.
So you just said we had to assume we were in equilibrium to use that.
To use this, yes. And give us
You know,
the,
that kind of hangs me up sometimes. When am I supposed to assume one thing and not the other? Or, you know, just, I don't know.
yeah, it's not a rote process.
Yeah, I was hoping you were gonna say it's not science. We should make fun of science.
I don't know if I have a good answer for you.
No, that's okay. I'm okay. I'm learning to be okay with not knowing things. That's what this class is all about.
Not knowing it.
At least for me, anyways.
Maybe we could make a movie like, there's already a movie called Knowing.
Oh, really?
Yeah.
Is it good?
Yeah, it's excellent.
What's it about?
It's Nicolas Cage is a single father whose daughter, or no, whose son starts scribbling down these things. It's just a series of numbers. And he finds out later that a bunch of kids are doing this. And the mystery is, what do those numbers mean? And he eventually figures it out, that they're dates and times of major events. And eventually, well, I don't want to give you away the ending. But knowing that information is the key. Not knowing, I don't know how that would fit into a good movie. It probably wouldn't.
Oh, I'm sure someone out there would be entertained by it. Humans are endlessly.
Comedy.
Yeah, there we go. It could be a comedy.
It's a comedy.
Throw in a love interest and you have a movie for the masses.
I had a question on 32 on how it was worked out. How did you go from the 13.455 to the 6.7 times 10 to the 5th? Because I can get down to that part, like I can work it out here. I just don't
okay.
see how you go from there to the
Okay.
answer.
Where are you at? Question?
On 32.
32.
On how it was worked out. I just can't get from that point to,
Right.
to the answer.
I'm not going to do the whole problem. I just want to, this is our reference point.
There he is.
Here it is.
No books, pens, papers.
I got here when I realized that my bag wasn't in my car.
Oh. Well,
So we determined that delta G was minus 33.336 kilojoules.
let me save you some confusion. That is version 2.
Per
We're
mole.
working through version 1. You don't-
And then we want to use this equation to find out what K is. All right. So we end up with log K is equal to this value after we fill in all these other values. And this, of course, delta G has to be 25 plus 273, which is 298. Okay, that's how you know what T is, because of this little zero. And then R is going to be the one with joules in it, 8.314. Okay.
That's 8. It's joules per mole K.
Joules per mole K, yeah. Joules per mole. Okay, for this one. And then this is your T. And then once you resolve those values and solve for log K, putting log K over by itself and everything else on this side, then we want to find out how you do K. Ln is the natural log, which is the base is E. Right? So we want the anti-log of this number. And all that means is the base to that power. Okay, that's how you resolve anti-logs. It just means that this is the power of that number that equals that number. That's what logs are. So you just have to be sure and find that one on your calculator. Mine has LN for natural log. And then you look for e to the x.
So let's see, how would we type that in? Would we type in the function first and then
Sure.
say 13.455?
On algebraic calculators,
I get 6.97.
I departed from algebraics long ago.
I've heard that.
I don't know, is this an algebraic calculator?
Yeah, they all are. If it's not a Hewlett-Packard RPN, it doesn't say RPN on it, then everything else is algebraic. Actually though, not Hewlett-Packard, but Texas Instrument makes one that will convert back and forth. You can use either, which is interesting.
Well, I did get the right answer, so
Okay,
that's promising.
so you must have done, yeah, just remember that process.
What's the thing there is, it's
Is yours not working?
working, I got it now, it's just
Okay,
getting to that point.
so that would be, where is it? 6.97 times 10 to the 5th.
So we calculated the equilibrium constant. That's what the big K meant.
Yes, that's the equilibrium constant for that reaction. And it's equal to just like this. Right. So when we were studying equilibrium by itself, we were using things like this equal that number. But now we can use the thermodynamics to determine what this is. And then once we know that, we can use that expression to do whatever else we want.
So,
Let's be positive, let's call this an upward spiral. I was just thinking the downward. It's like, be positive, Stephanie. Upward spiral.
so
I
what
was
is,
thinking like how the informational circles back around.
why is there a version 2?
You know what?
Just,
I think
so
it's
I'm
punishment for
trying not to
being late.
overload
Doesn't
you.
get to know.
at one point, both of them were together.
Oh, that would be overwhelming.
Yeah, and the first time I tried that, my
Slightly
students'
abusive.
heads exploded. So I split it into two and just give you one.
Understandable.
So what, this is just another,
It's another set of fun activities.
It just gives you a lot more practice.
do what practice?
I will look at a couple out of version 2. That's why I gave you the copy this time, so you wouldn't have to write all the stuff down.
Oh, hey, did you guys talk about the test yet? Did you get yours back?
I haven't turned mine back in yet.
Oh, I just wondered if there was any.
Working.
Since all of my stuff is at home, I'm gonna, I don't know, you guys will come up here maybe tomorrow, if that goes to work and it's, they'll just slide it under your door,
The lab.
the test.
The big bomb.
The one that,
Oh, that one, yes.
Well, if they haven't turned theirs in, I guess there's no discussion at this point. Wouldn't worry about it.
I guess I can scan it, so I can email.
Were you gonna do another one? That was it, wasn't it?
Yeah, no, I'm good. I don't want to do any more.
Okay.
It's
Yeah,
just,
these I've been carrying around forever. All right, there's a lab report due today too.
you have questions about that.
Okay, so let's get back to business. What about, did 34 give you trouble? Or was it just sort of murky water and not muddy?
Just forgot to do 2 sections. laboratories.
For the following reaction, carbon dioxide plus water yields methane plus oxygen. The delta H is equal to 803 kilojoules. Right, so that's positive, means it's endothermic. So in order to get this to go over there, you got to add energy. So which of the following will increase K? What does K look like? Well, historically, we had K like this. And CO2. Oops. Water. Okay. Now, some of them we can do without using thermodynamics. What if you decrease the number of moles of methane? Oh, the question is, if we want to increase, what will increase K? Will changing the moles of anything decrease moles of methane? So which one's methane? That one. That's methane. If you decrease the number of moles of that, will it change K? Nope. It may change the equilibrium position, but it will not change K. Right? So that won't change K. Increase the volume. So increase the volume. Will that change K? It'll shift the position, but it won't change K. Right? If you increase the volume, you've got 3 moles here and you got 3 moles there. Actually, you won't even change the position, right? Because you're not changing the moles. And well, shortly, he says, there's no disturbance there. How about C? Increase the temperature of the system. Increase temperature. What effect will that have on K? Well, you know from previous chapters that that's the only way you can change K, is change the temperature, right? So it will change the temperature. Question is, will increasing temperature, oh, wait a minute, what is it? Let me go back to the question. Will increasing the temperature increase K?
With drive the reaction to right.
Yes.
Which would make the number on top bigger, which would increase.
Right. So that's one way. It's endothermic. Which means reactants plus delta H yields products. So increasing temperature will drive to the right, which will increase products, which will increase K. That's true. Right? The way I approached it in the review document was a little more complicated, I guess. If we plot log K against 1 over T, you get a straight line with a slope of delta H over R. If you, the log of K will increase as K increases. So that means that according to this graph, if you increase T, temperature, you will decrease 1 over T. So as 1 over T decreases this way, we increase K. Right? We just need to decrease this one, which is the same as increasing T. And to decrease this one, we got to go this way. So that way increases K. That's just another way to look at it, but actually, if you're in the middle of a test, your way is quicker. Let's see. While we're on that topic, let's see. Oh, they're over here. Version 2, number 53. Version 2, 53. Uses that graph to answer the question. So I figured since we're on that topic, we'll look at version 2, 53.
I think maybe 52
Sorry?
is the one with the graph,
Yeah, it's got a graph.
would be number 52.
Oh, 52? Okay. Yeah, you're right. The one with the graph. Okay, so the question is, we're given this graph for our reaction. And we've got 1, 2, 3, 4, 5. So this is 3 there. And then it goes out to 0.2, 0.1. So this goes like that. That's the graph of our 1 over T versus K. So the question is, what's delta S? So we need to know what that graph represents. Actually, I don't see delta S in either one of these, so it must be in the slope. Right, so what's the slope of that line? Here. Oh no, I'm sorry. Here. Not in the slope. This is the description of that one, minus delta H over R times 1 over T. Okay, so the slope is actually this. The slope is minus delta H over R. Minus, that makes sense because it's going like that, and not like this. And the y-intercept this. So the y-intercept is here, which is 3.0, and that's equal to delta S over R. So it's a matter of interpreting the graph. Yeah. What does this mean? What's the line that describes this? And you're interested in this part right here. because you can read off the graph that this is 3.0 and that's equal to this one. So now all you have to do is divide by 3145 equals 3. Then you just solve for this one.
How does it become a -3? Or am I just not seeing that?
Oh.
It's just an equal sign.
Yeah, that's just an equal.
Okay, I always thought you wrote negative.
Sorry.
I just make sure I understand.
There you go. And then delta S divided by, let's see, what is this? Delta S over R. Eight into 3. Okay, delta S delta S for the reaction in joules per mole, K. So the delta H is usually in kilojoules. I think that's what's got me puzzled. Because if you divide 8 into 3,
Wouldn't you be multiplying?
oh, multiply, oh, shoot, thank you. Yeah,
I was about to say, because one of the answers is 25, so.
Yeah.
that makes sense then. And, right, that won't work unless all the units are similar. So it has to be joules. Okay. I confused
So how
myself.
did you know, I guess,
No, what?
just on the graph in general, like how do you know that the y-intercept is that change of?
This one, the way the equation is written, this is y, this was mx, and this is b. And b is always the y, the intercept. Straight line. That one, that one, that one, this one.
Oh my goodness. So which class did I miss here?
This is
Geometry.
geometry, trigonometry,
Which class?
Y, well, x plus b is just algebra.
algebra. Yeah, that's right,
This
it's
is just
algebra.
basic algebra from when I was a sophomore in high school.
Yeah, probably.
Yeah. Okay.
Yeah, it's
My
been
bad.
around for a while.
I mean, it does look familiar. It's just, I'm like, where should I pull this out of my brain from?
Right.
Maybe I should have taken an algebra refresher. Or chemistry. No.
Well, I don't know, now you know. Scientists always try to squeeze a straight line out of their data. It's much easier to deal with if you can define a straight line, even if you have to jump through these hoops. Like that one's log and this one's inverse. But we'd rather do that than try to deal with a curve.
So B is the y-intercept.
Yeah, it's this one right here. The reason it's the y-intercept is x is 0. So if this one is 0, that term drops out. And this y value is equal to that value. So whatever y happens to be, in this case 3.0, is equal to what's left over here over r. Okay, and y is equal to log k. We could find out what k is from there, right? At that point, we just solve for k. But that's not what we're interested in. We're interested in delta s. So we just say this part equal to that part and solve for delta s. You also need to know which r to use. We've only used 2 different r's.
The gas one.
Yeah, 0.08206 liter atmospheres per mole K instead of joules per mole K. Okay, that was version 252. Just following up with version 1 using that graph. We can go back to version 1 now if you like. Over there.
Would you say that these are more challenging questions or
They might give you a different perspective. Yeah. I'm doing all the time.
9, 14?
Okay. No, 1025 is when we
I was like, did I mess up my watch?
officially over. Yeah. No, power went out of my house, so but my watch is on battery, so I'm okay.
It was annoying having to go around and reset all the clocks.
Yeah, you lost power too.
No, I'm just saying when it does happen, having to go through, the stove and the microwave and the.
Any wall clocks you have?
I don't think it happened.
No.
Most of the time, of course, we really need time the stove and the microwave or just our phones. Because, we're all attached to hips to our phones.
I wait for the cable to come back on and then check the clock on there.
Mm-hmm.
Auto sync.
Really not a fan of this weather right now.
Do what?
Really not a fan of this weather right now.
No.
It was like the more as I was driving here, it just kept getting progressively worse. Because it wasn't snowing in Ballard.
Okay.
Can we go over number 53 on version 1, just because it's more of the discussion and
Okay.
that kind of information.
53. Okay. Which of the following statements is correct? So for this reaction, yields 204. The delta H is over here. Delta H is minus 50.8 kilojoules. Delta S is minus 175 joule per K. I have a sneaking suspicion we're going to need to do this anyway. And '53. I have the same. Am I looking at the wrong one?
That's correct.
That's the one we're on, right? Which of the following statements is correct?
Yeah.
I wonder if I worked out the wrong problem. No, I mean, there it is. I'm trying to say, how does this answer the question? Q is greater than K, equilibrium shifts to the left more. Okay. All right, so A choice is sum N2O4 decomposes to NO2. Goes backwards that way. Okay. B is sum NO2. New word.
Yeah.
Dimerizes to form N2O4. That just means we put these two together and make that. It dimerizes because it's like this. Right, and you get two of these together and they hook together like this. Right. So here's our monomer and here's our dimer. Because you have this one here and this one here. That's all that means. Okay. It's just more blue smoke. C choice is systems at equilibrium. Okay, it's becoming clear to me now. And D is final pressure needed. To answer the question. And E is none of these. Okay, so if we want to know which direction the reaction is going, which is what this is saying, is it going this way? Is it going that way? Or is it sitting still? And the way to answer that question is find out what Q is. So, in order, there's more information given, excuse me. Initial partial pressures. All right, so for this one would be 2.4 atmospheres. And this one is 0.42 atmospheres. Okay, so we can calculate Q from these values, but we need to know what K is. So let's see what information we've got here. We have delta H, delta S, and they're at standard temperature, so we got the temperature. Right, so the temperature is going to be 298 K. That's 25 degrees centigrade. Right. So we can calculate delta G from this.
With negative RT natural log, or no, we don't have K.
So this will give us delta G. And then delta G is related to K through this equation. And that should be in useful information.
Wait, where's that you're using?
Hold on a second. Let me be sure I gave it to you. Okay. Lower right-hand corner, delta G equals delta H minus T delta S. That's given. And then delta G equals RT log K is in the column to the left of it. Okay.
Oh, okay, I found
Right,
it.
so
I was
there's-
looking for the delta G equals delta H.
There's Gibbs free energy equation, and then down here, just a little bit there, is the other one. We eventually have to get to K. Now, when I did it here, I combined the both of them and then did one calculation. But you can do this calculation to find delta G, and plug it in here and find K. Right? So why don't we do it that way?
Mhm.
We've already done it. I've already done it combined equation here. So let's do this one and find out what delta G is. Delta H is minus 5.68 times 10 to the 4th joules. And then T is 298 K times minus 175 joules K. Okay, so delta G0 equals, say, 298 and 175. So this one is 52,150 joules. That's K cancels. And that's a positive, right? Negative, negative makes it positive. And this one is, so we just combine those. Oops. Right. So I get minus 4650 joules. Delta G0. Then if we equate that one, minus, and the R is 8.1345, I think, isn't it? I'm trying to remember. 3145. 3145. And then temperature is 298. And then log K. There you go.
Right, minus 4.6.
And then this one is going to be that one divided by this one. So I'll write it out like that first. Minus 4650 divided by minus 8.3145. 8. And that's I did that right. Did I do that right? 0.12027. No, I didn't do that right. We do this one first. 8.3145, 298. Okay, I did something wrong. How about this one? Did I do that one right? Kilojoules. Yes. That one's right. 298 times delta S 175. Did I write that one correctly?
Maybe, well, you moved the decimal place, is that correct?
Here? Or here? Where?
Should it be 4.65?
Here?
No, she's talking over there, I'm looking at.
Here? Here?
Yeah. Don't show me more
Okay,
problems.
that's right. That's right. So let's see if I did that one right. 298, 175. That's correct. And this one. Okay, that's what I get here. 4650 joules. And then this is minus 4650 joules. And this is R. And this is, that's where I made my mistake. No, it wasn't. That's right. 298. Okay. Because this is joules. Per mole, K. K's gone. Joules per mole. What is this expression right here? 8.3145, 298. So this one is minus 2477. Okay. $1.877. There we go. Did I lose you? Or I was putting you to sleep? Should I stop and back up? Are you with me so far? What Joyce would say. What did Joyce say? Are we together?
Yeah, we're together.
And then K would be E to the 1.877.
So we get that, we say this function to 1.877 equals 6.53.
Okay, now that we have K, let's calculate Q. That will tell us which direction the reaction's going. So Q is going to be N2O4 divided by 2.4 squared. Oops. 4.
So I guess I forgot equilibrium. You could use pressures for,
Yeah,
in replacement of concentration amounts.
well, let me see.
Is that on here?
Did I got it backwards. I need to read the problem again because I think I put the wrong numbers up there. 53. .4 atmospheres is N2O4. I get it backwards. Okay. You know, that's a good question. Because if the units are atmospheres, you get 1 K, and if the units are molarity, you get a different K. And they're related. They're related by, where is it? Here. Is that right? They're related by this equation. So that's a bad question. Because it doesn't say what your units are for K. Let's see. Right, it doesn't. We don't know if this K is related to concentration units of molarity or to pressure units. You have to assume, here we go again. You have to assume because this is gas and that's gas, that this K is going to come out in pressure units.
So let's assume that, and we got Q as 13.6. I did the math.
Okay, right, we need to put this one
But-
on top.
Yeah.
$13.6.
We got Q is greater than K.
Q is greater than K. So if Q is greater than K, that means that this value is bigger than that value, which means it's going back this way. A. Because Q is greater than K. It's going back from this one to that one.
That was a whole lot of effort to come back to that answer.
Yeah. That looks like a good bonus question. Or break it out and say, if you're given this information and you're also given this K, you don't have to calculate it, then answer the questions. And that cuts out all of this crap right here. And then all you have to do is calculate the Q and compare it to the K and answer the question. That would be doable on a test.
I mean, how much time did it just take you to go through it? You already know how to do this.
Yeah, right. So that needs to be abbreviated for test taking purposes.
Or bonus.
Yeah. Or just excerpt a part of it and change the question. And just calculate the K.
And why did you write that up there?
This one,
Yeah.
I was wondering if these values, if this K were in terms of concentration, then you could calculate what the K was in terms of pressure and compare it to this one, because this is in terms of pressure. But I'm assuming that since this is gas and that's gas, that the value is going to come out already in terms of pressure. Let's see. There's a short one. 59. That one doesn't take much in the way of, this is really, do you understand what it means? It doesn't even describe the process, it just gives you the information. So we've got a temperature of 300 K. We've got a delta G of 10.4. Delta H minus 7. joules. So we're saying the process is carried out reversibly. We talked about that, didn't we? Most reactions are irreversible. But in order to use thermodynamic concepts, we have to approach the reaction in terms of, in a way that it's reversible, which means you have to narrow your conditions down so that it can go backwards and forwards. And that means that the change has to be very small, right? So the theory is, if the changes are very small, then your reaction is reversible. And that usually means over a very short time scale. So that's what they mean here by carried out reversibly. The amount of useful work that can be performed. All right. So what's the amount of useful work? You remember Gibbs' approach to the problem. He wanted to know what's the maximum amount of useful work you can get out of a reaction. And that's when he came up with this one. But he equated this free energy to the amount of work that you can get, actually negative. No, it's actually equal to work. Negative is a different approach. Okay, so the concept is that is the maximum amount of useful work you can get out of this process. It's equal to the delta G. And since it's a negative, the reaction is spontaneous, and you can actually extract work from it. If it were positive, then you couldn't get work out of that reaction. You'd have to put work into it to make it go. But it would be spontaneous if you reversed the reaction. If you went instead of this way, or that one, if it were positive, you just have to go the other direction to make it spontaneous. And then you could get work out of it, because you can't get work out of a non-spontaneous reaction. You have to put work into it.
So delta G is defined as a change in work?
Yes. Yeah, delta G is equal to the maximum work available from that reaction. And then you have to understand that there's no such thing as, you can't arrive at the maximum work. First of all,
So,
if you know the enthalpy, you can find out the maximum work by removing the entropy change. But even then, lack of efficiency says that you'll never get to that one anyway, because you're going to lose something in the process. And it's not just entropy that you lose.
So the answer is.
that's rule number 2, you can't even break even.
Right. That's right.
So, so here for this question, really, we're just looking at the delta G, so the answer is reversibly still 10.4 kilojoules.
Yes, it's just negative 10.4.
And you said you can't get work out of a non-spontaneous reaction.
Right.
You have to add energy back to get something out of it.
Right. So with the wording there,
So because this is a spontaneous reaction, you can get work back out of it.
right, the amount of useful work that can be performed, that means that it has to be a negative delta G. So that disqualifies E right off the bat. So it's a positive.
I'll move right on to the under 60s right there.
60?
You know, if there were volcanoes in the question, we should definitely do that one.
Okay.
Sarah laughed, come on.
When ignited, solid ammonium dichromate decomposes in a fiery display. Okay, that's true. Means it's exothermic. This is the reaction for a volcano demonstration. The decomposition produces nitrogen gas, water vapor, and chromium-3 oxide. And we're going to hold the temperature constant at 25 degrees. I doubt if in reality it stayed there. Right. But for our calculation, we need to hold the temperature constant. Determine the delta G for this reaction. All right, so in that case, let's see, do we need, did I go overboard? Oh, okay. I see why I did that. That's because I combined 60 and 61. And 61 is going to need, let's see, 60 calculates the delta G, and 61 calculates the delta S.
Mm-hmm.
Okay. No, you really don't need the equation. I don't think. Hold on a second. Yes, you do. Yes, yes, you do. Because we've got to, we're going to use the standard entropy, standard enthalpies, and they have to be multiplied by the number of moles. Okay. So we do need a balanced equation. Ammonium dichromate. So you got to be able to write that. Ammonium, and then dichromate. And that should be in useful information, polyatomic ions. If it's not, I'll have to give it to you. It's not. Okay. So you're within your rights to ask me what it is. So ammonium dichromate, and this is 2 minus, so that means this one has to be 2 there. This is a solid. And it decomposes into nitrogen gas and water. H2O. At 25 degrees, it'll be a liquid. And then that's chromium-3 oxide. That's not a gas. That's a solid. Chromium-3 oxide.
Oh, well, it's marked as a gas.
I know. That's not right. It doesn't call it a gas, does it? No, it just says chromium-3 oxide. Chromium-3 oxide is not a gas. That's a solid. I don't expect it'll have a bearing on the answer. It's just an error. Okay. And this occurs at 25 degrees C, which is 298 K. Now let's see. We've got to be sure it's balanced. 2 chromium, 7 oxygens. So 4 here and 3 there is 7. 8 hydrogens and 2 nitrogens. So that's balanced. We just need a 4 in front of the water. All right. So we're given the enthalpies of formation. So the delta H for the reaction is going to be That one's 0. So this one's going to be 4 times water,
Oh, why'd you say 0?
because we're doing enthalpies. And that's an element. Enthalpies for elements are always 0. And it's in the chart too. And water is 4 times minus 242 kilojoules per mole. And then chromium chromium 3 oxide is minus 1147 kilojoules per mole. Then we subtract that one. There's one of those. So that one is, oh, you just let me talk. It's right there. The formula for ammonium dichromate. So you don't need that. You don't need the polyatomics. Okay, so this is going to give us minus 2.093 times 10 to the third kilojoules. Okay. Delta S, why are we doing these? Well, delta S answers the question for 60, but we need delta H to answer the question for 61, I think. No, 61, this answers number 61, right here. And we need that one to answer 60. So this one's going to be, nitrogen is 0.1915 joules. And then 0.1187 for water. And then chromium 3 oxide is one of those, which is 0.08118. Right. Then we subtract ammonium dichromate entropy, 0.113. Is that? Right.
Are these numbers given?
Yes.
Yes, right. They're right there in the problem. And these, this is unusual. The entropy is given in kilojoules. That's why it's these decimal numbers. Normally it would be in joules and you'd have to convert. But we're being kind. And this is 0.6338 kilojoules per K. Now we can calculate delta G. Question?
Yeah. So in calculating enthalpy, the elemental nitrogen is 0, so that's why that's not in there.
Right.
And the entropy, the elemental nitrogen does have amount.
Right.
So that does appear in some of the products minus some of the reactants.
Right.
Okay.
So delta H is minus 2.093 times 10 to the third. And then we're going to subtract temperature, 298 times delta S, And that should be equal to, check myself here, 2.093. Let's try that again. $298.63. And I get minus 2282. Kilojoules. So this answers 61 right here. And this answers 60. That's why I put them together. But if you don't balance the equation, you'll never know to put that one there. And never know to put this one here. So we've got to balance the equation.
So 0.63.
Okay, I did get that. And then to go back to 60, we needed the delta S
Yeah, I need this one.
and the delta H. So delta.
So the current state of things, you want to go on for a while? We only have 25 minutes left in the line anyway, but it would give us a jump start just in case it gets worse.
Oh, it is.
I mean, unless of course you have some other questions that you want to ask.
Okay.
I don't have part one, so.
Let's see.
I did not get the right answer for some reason.
A lot of decimals there.
Yeah.
Can I have one more second to see what I did
Yeah,
wrong
sure.
here? Times.
This test will be next Monday.
Uh-huh. And then
And final,
chapter 18.
is that just the final chapter? Or do we still have another couple of tests?
Chapter test, 18 is the last chapter test. Oh, that's the last test.
What am I doing wrong?
We're not doing it fine.
I'm not getting the same answer as you.
Using these values?
Mm-hmm.
Okay.
I've gotten two of the wrong answers.
Right, this should be minus 2093.
Oh, that might be it right there. I didn't put the negatives. I have it over here, but then I didn't put it over here. That might be the problem. Let me do it one more time. Negative number. Now I get the right answer. Finally. Do you want to go ahead and start? I'm okay with that. I actually have some questions about the lab that's due. I brought my computer. I'm terrible with Excel and I need help setting up my graphs. So. After we do today's lab, if there is some availability, that would be great.
Yeah, if you've got time before my next class. Or after my class.
Can I have the papers for the lab today?